ஓகே. சோ எனி டவுட்ஸ் இல்ல, நீ படிச்சிருவல கிஷோர்?
எஸ் மேம், படிச்சிருவேன் மேம்.
ஓகே ஓகே ஓகே.
ஓகே.
ஸ்வேதா? ஸ்வேதா?
எஸ் மேம், இருக்க மேம்.
ஓகே. எனி டவுட்ஸ்? மெதுவா படிக்கணும், ஓகேவா? தட் இஸ்
ஓகே.
ஃபினிஷ் பண்ணதுக்கு அப்புறமா, தட் இஸ் முடிச்சதுக்கு அப்புறமா யூ வில் அவங்க செஷன் முடிச்சதுக்கு அப்புறம் queries முடிச்சதுக்கு அப்புறம் vote of thanks. ஓகே, நான் சொல்வேன் கால் ஸ்வேதா சொல்லிட்டு, சரியா? ஸோ கிஷோர், பிரியதர்ஷினி பிரியதர்ஷினி
எஸ் மேம்.
ஓகேவா? கொஞ்சம் சத்தமா பேசணும், மெதுவா பேசணும், சரியா?
எஸ் மேம்.
சரியா? நான் வந்து ஸ்வேதா கிஷோர் முடிச்சதுக்கு அப்புறமா நான் வந்து கால் அப்பான் பிரியதர்ஷினி டு இன்ட்ரடியூஸ் அவர் சீஃப் கெஸ்ட் சொல்லுவோம், ஓகேவா? ஸோ
ஓகே மேம்.
ஓகேவா? ஸோ உங்க பேர் சொன்னதுக்கு அப்புறம் வந்து அலர்ட்டா இருங்க, சரியா? அலர்ட்டா இருந்துச்சு இது பண்ணும், ஓகேவா? ரெடியா?
எஸ் மேம்.
சரி.
மேம் டைரக்டா இன்ட்ரோடக்ஷன் டு அப்படியே படிக்கலாமா?
இன்ட்ரடக்ஷன் டு சீஃப் கெஸ்ட்னு இல்ல, மிஸ்டர் சுப்பிரமணி துரைக்கண்ணு அதுதான் ஆரம்பிக்கணும்.
ஓகே மேம். ஓகே மேம்.
சரியா? பாஸ் விட்டு மிஸ்டர் துரைக்கண்ணு has been working as அந்த மாதிரி படிக்கணும், சரியா?
ஓகே மேம். எஸ் மேம்.
இன்ட்ரடக்ஷன் டு சீஃப் கெஸ்ட் எழுதி படிக்க வேண்டாம், அது உனக்காக எழுதி கொடுத்தது.
இல்ல மேம், குட் மார்னிங் டு ஆல் அந்த மாதிரி சொல்லலாமான்னு கேட்டேன்.
குட் மார்னிங் ஆல் சொன்ன ஒன்றும் பிரச்சனை கிடையாது, தப்பு இல்ல.
ஓகே மேம்.
வந்து ஐ எம் பிரியதர்ஷினி டு இன்ட்ரோடியூஸ் தி சீஃப் கெஸ்ட் நான் சொன்னேன், தப்பு இல்ல, பிரச்சனை.
ஓகே. எஸ் மேம்.
சரி. ஸோ நீங்க 3 பேருமே கிளியர், ரைட்டா? ஓகே. இஸ்ரேல்
சொல்லுங்க மேம்.
என்ன ஹோஸ்டா மாத்தீங்க. சார் வந்துட்டாரு. சீஃப் கெஸ்ட். கிஷோர், பிரியதர்ஷினி உங்க கிளாஸ்மேட்ஸ் எல்லாரையும் இமிடியேட்டா வர சொல்லுங்க சீக்கிரமா. ஓகே.
Yes, ma'am.
ஸ்வேதா. ஓகே ஸ்வேதா.
Yes, ma'am.
ஓகே, எல்லாரையும் வர சொல்லுங்க. ஓகேவா? கேர்ள்ஸ் எல்லாரையும் வர சொல்லுங்க, பாய்ஸ் எல்லாரையும் வர சொல்லுங்க. சரியா? இட்ஸ் டைம் டு ஸ்டார்ட், ரைட்?
Okay, ma'am.
சுப்பிரமணி சார், நீங்க இப்ப ஓபன் பண்ணலாம். ஆக்சுவலா ஷேர் ஸ்கிரீன் பண்ணலாம். செக் பண்ணிக்கோங்க.
ஓகே.
உங்களுக்கு கோஹோஸ்டா போட்டுட்டேன் நானு. ஷேர் ஸ்கிரீன் பண்ணி.
ஆக்சுவலி இது டெஸ்க்டாப் ஷேரிங் ஆப்ஷன் இருக்காமா ஜூம்ல?
இருக்கு. டெஸ்க்டாப் ஷேரிங் இருக்கு.
அது ஷேர்
நீங்க ஓபன் பண்ணி வச்சிருந்தீங்கன்னா வந்து பண்ணலாம். இஸ்ரேல் ஜி, இஸ்ரேல்.
சார் ஷேர்ன்னு இருக்கும், அதுல ஸ்கிரீன் கொடுங்க சார்.
ஓகே.
இப்படி கொடுத்தீங்கன்னா டெஸ்க்டாப் ஃபுல்லாக நீங்கள் எல்லா ஆக்டிவிட்டிஸ் பண்ணுறீங்கன்னா எல்லாமே தெரியும்.
ஓகே. ஸோ இப்போ நான் ஷேர் பண்ணிட்டு இருக்கேன். உங்களுக்கு வருதா?
வருது. தெரியுது.
ஓகே. இன்னொன்று, இதில் வந்து வீடியோ ப்ளஸ் ஷேரிங் டுகெதர் நடக்குமா?
சாரி சார்.
ஸோ ஐ எம் கோயிங் டு ஷேர் மை ஸ்க்ரீன் ஆஸ் வெல் அஸ் ஷேர் த வீடியோனா அது நடக்குமா?
எஸ் சார், யூ கேன் ப்ளே இட் நவ்.
கேமரா ஆல்சோ?
யா.
ஓகே, ஜஸ்ட் a moment.
ட்ரை பண்ணி பாருங்க.
இதுல பேக் சைடு இது பண்ண முடியுமா? blur பண்ண முடியுமா?
புரியல சார். பேக் சைடு
blur பண்ணனும். பேக் சைடு என்னுடைய பேக் சைடுல என்ன இருக்குன்னு தெரியக்கூடாது. அது மாதிரி ஆப்ஷன் இருக்கா ஜூம்ல?
இருக்கு சார், பட் அது இனிஷியலி செட்டிங்ஸ் பண்ணனும். அது இப்ப பாசிபிள் இல்ல நினைக்கிறேன்.
ஓகே.
பட் ஏதாவது செட்டிங்ஸ் இருக்கான்னு உங்க சைடுல செக் பண்ணி பாருங்க சார், வீடியோ ஷேர் பண்ணும்போது.
ஜஸ்ட் ட்ரை பண்றேன்.
ஓகே. இந்த வீடியோலயே பேக்ரவுண்ட் இருக்கு பாருங்க. ஆக்சுவலி நீங்க ஏதாவது ஒரு வீடியோ
இம்போர்ட் பண்ணிடலாமா?
சார் சொல்லுங்க சார்.
பட் இம்போர்ட் எதுவும் பண்ண
நீங்க வேணா இப்ப வாங்க, வந்துட்டாங்க. நீங்க வேணா ஹலோ சொல்லிட்டு வேணா போங்க. வருவாரா? ஓகே.
ஏதோ டவுன்லோட் பண்ணி ஐ வில் ட்ரை.
பிக்சர்ஸ் ஏதாவது இருக்கா பாருங்க.
மோஸ்ட்லி இருக்காது, நாங்க எம்டியா தான் வச்சிருக்கோம். ஓகே, லெட் அஸ் டவுன்லோட்.
ஆன்லைன்ல டவுன்லோட் பண்ணுங்க.
வாப்பா மோகி வா. தெரியாது. இப்போ ட்ரை பண்ணுவோமா ஸ்டார்ட் வீடியோ? எஸ், பட் இப்போ என்னன்னா என்னுடைய லேப்டாப்க்கு நான் இப்படி இருக்கேன். ஓகே, ஜஸ்ட் ஓகே ஃபைன். தெரியாது.
Subramani sir, everything is fine for you?
Yeah.
Yeah. Okay. So we will wait for 5 minutes. Almost 60 participants are there. 55 to 60. So we'll wait for 5 minutes to join.
Okay. So are you getting my screen?
Yeah. I can see your
Okay.
screen.
Okay.
Shall we start, sir? Shall we start?
Yeah.
Yeah. So, good morning, one and all present here. I warmly welcome you all to the webinar on process equipment design using softwares. It's a great pleasure having you here, sir. Now I request Kishore of final year to deliver the welcome address.
Good morning, ma'am. Coming together is a beginning, keeping together is a progress, working together is success. Good morning to one and all present here. I am Kishore of final year chemical engineering. It gives me a great privilege to welcome you all to this webinar on the process equipment design using softwares. On this occasion, I extend my cordial welcome to our distinguished chief guest, Mr. Subramani Duraikannu, Senior Process Engineer, Warli, Saudi Arabia, for accepting our invitation in spite of his busy schedule. We are proud to welcome our proud alumni to open up our minds for a session on designing of equipment using various softwares and exploring ourselves to the recent developments of chemical engineering. I welcome you, sir.
Thank you.
I would like to heartily welcome our HOD, Dr. S. Dinesh Kumar, to this webinar. I extend my warm welcome to our coordinators, Sheba ma'am and Israel sir, and all our staff members to this occasion. I would like to extend my warm welcome to all the participants from various colleges to this webinar. Without any further ado, keep your fingers crossed for this session. Thank you.
Thank you, Kishore. Now I request Priyadarshini of third year to introduce our chief guest.
Good morning, all. Myself, Priyadarshini from third year chemical department. Now I am going to give a short introduction about our chief guest, Mr. Subramani Dunaikannu. Mr. Subramani Dunaikannu is currently working as a senior process engineer at Worli, Saudi Arabia, with 14 years of experience in conceptualization and feasibility studies, basic engineering field, detailed engineering in the field of refinery, upstream facilities design with offshore and onshore, oil and gas processing, NGL, fertilizer offset and utilizers projects. His extensive knowledge on process design software includes Aspen HYSYS, Aspen Plus, Aspen FlowNet for Relief System, HCR, PipeNet PSVS, and SPPID. He is expertise in various fields of refinery with gas processing plant facility design, equipment sizing, specification of packages, and lot more. He has headed as lead process engines and principal process engineer in various design companies across India and abroad, which includes Worley Parsons, Technip, etc., with the successful execution of all projects with his intense work assignment and has produced deliverables with collaborative work. His professional membership includes member of Saudi Council of Engineers, Society of Petroleum Engineers, Indian Institute of Chemical Engineers, ICHEME. Last but not the least, the speaker is a proud alumni of St. Peter's. It is my great privilege to welcome our distinguished speaker of the day to take over the session.
Good morning. Thank you.
Thank you, Priyadarshini.
Thank you, ma'am.
Now I request the chief guest to take over the session.
Okay, thank you, Priyadarshini and Shiba. It was a good pleasure. It's my pleasure to give a training or webinar to my juniors. As Shiba was saying, I'm 1 year senior batch to Shiba, and Dinesh sir and all were my earlier professors. When I was doing my chemical engineering at St. Peter's, they were my professors. Good morning, sir, and good morning to the team. So let us start with our webinar. So today I'm going to present a session on process equipment design using softwares. This is a very big area of design. Every day we are doing, I have a 14 years of experience. Still I'm learning on some equipments. Here I will be giving an introduction and basic concepts and various softwares the juniors and the college students has to learn before entering into a design field, EPC field. So as a chemical engineer, when I was doing, there are many options. We can be an operator, we can be a design consultant, and we can be a professors. But the one I chosen is a design. I had an opportunity, so I joined here. I prefer the people to join here where you can explore more. You can apply what you are learning here, what is implemented there. You can see the design once it's commissioned and it's working. And sometimes we can see it's not working and it creates a damage to main material. There are many failures in our designs also. These are the lessons learned, we do that. So let us start our session. So the session will be going like this. I will be giving an introduction and process design engineering softwares and codes and standards, general engineering design phase and the approach we do. And I will be giving an example. In this example, you can learn some equipment sizing, pumps, columns, vessels, lines, we do that. These four I would like to cover here. So equipment design is art, it's not a science. We need to have a process equipment which satisfies the process needs, and it should serve the process demand. For that, we can have any kind of size and we need to have optimum because it's our cost. Finally, somebody is going to purchase and it has to perform. So it's an art. And when compared to science and our engineering, engineering needs the reality and it has to be implemented in the provided space in the plant. It may be a green field or a brown field. To going into that, what is green field, what is brown field? Green field is the area we are going to construct a new plant, new process plant. So we are provided with a lot of area, but in a brown field, we cannot. Already some plants are there. We are providing some more equipments, maybe to improve the quality or quantity of the process plant. In that time, it's art. We need to provide a small, always people prefer small. We cannot say small, it's optimum. So it's art, no science there. Okay, engineering design is a process of diversifying system component and process to meet desired needs. And equipment design, I cannot say equipment design, it's a process design, I can say. It is a process of calculating and providing specification to purchase a component in a market. So our design should come into a reality. So we cannot provide some specification or some calculation with science to purchase in a market. We cannot purchase. Then it will be another research where the people has to do it. Like we are finding an vaccination for COVID-19. It is a research. But if you have another previously known diseases, we have medicine for that. Same way we need to provide. Our design, when come into the market, we need to purchase the equipment and to install and commission. And we need to have a proven record. Whenever we size or choose any equipment, it should have a proven record of good performance. It should not be a new one. We are going to do innovations, and client will not like that. Client will say us, no, you are providing a new design, which we don't want. We don't know about the safety of that. And we don't know about the performance. They want always the proven designs only they expect. So normally the equipment designs are done by 3 agencies. One is a process licensor. The process licensors are like UOP, Accents, they are big shots. They design the process scheme. If we read our sheaves, we have many processes to produce ammonia. We have many processes to produce any chemicals. So they are the licensors. They are taking care of the patented designs, such as reactors. They do have a pilot plant. They do have a pilot test, and they do have a catalyst proprietary. So these equipments, only the licensor can do it. If we are a process engineer, if we are with the licensor, yes, we can do a reactor, and it's our guarantee. And most of the process engineerings are done by licensors. They finalize what is the performance. And the engineering contractor design, this is non-licensed equipments, open art. We can do vessel, pumps, column, heat exchanger, compressors. And majority of the equipments are sized by contractors. Licensor do only the proprietary items. And other designs are vendor supplied items, such as distillation column trays, column tray arrangements, how many bubbles we need. These are all by column tray vendors. It's not by us. And some other auxiliary systems are there: pump seals, compressor seals, ejectors, steam traps. These are all vendor supplied items, which we cannot do it. And we don't want to do also. These are all proprietary, and it's all auxiliary items. So most of the EPC contractors are doing the middle one, the engineering contractor designs, we do that. Okay, so why do we need a process softwares? These are the softwares with inbuilt chemistry and physical formulas, principles, and with the database to easy and fasten the design completion. We don't want to do any research. There are a set of rules and standards. The only thing is going to change in every project is feed and the location. Once a feed quality change, then we need to change. The chemistry and physical formulae and principle remain same. So softwares are built for that, and the softwares are open to all process. So what I recommend for a beginners is that I'm going to list some of the process engineering softwares which converts a chemical engineer into a process engineer. So for us, let us start with the simulation software. Maybe you may be knowing simulation. What is simulation? Simulation and modeling, in fact. Simulation is one activity, modeling is another activity. Here I have missed to list a modeling, but we can do it with the Aspen ISIS. I hear that Priyadashini was reading HYSYS. No, it's Aspen ISIS. And one of the important and significant software of any chemical engineer. It is I can say it has 100 times of Piri. Piri is having most of the chemical engineering principles and databases. Sometimes it has some catalyst data also. This Aspen IC software is the software which is a beginning to any chemical engineer to want to be a process engineer. We don't need to read Peri if we are familiar with HYSYS. And the next one is Pro 2. Is another equivalent software, but it is mostly used for refineries. Aspen ISIS is used in oil and gas. Again, what is the difference between refinery and oil and gas is the nature of the chemical. Refinery we handle pure. After crude oil, all are pure. But in oil and gas, it's not pure. We may get sand, we may get salt, we may get produced water. So Aspen ISIS is generic and the beginning. If you want to get specialization, we can move into a Pro 2. And then there is a Promax. This is a tool meant for electrolytes. Some of the chemicals, if you read our Gibbs Energy, Ping Robinsons, these are all having some limitations. So these limitations are put into a place of Promax. So the Promax will handle electrolytes, salts, sulfur, amines. Amines are not, amines chemical nature is different from crude oil and water. So Promax is specifically meant for amines. So it's based on the nature of the chemical, we need to select the software. And thermal sizing, people may know that there is a HTRI and Aspen EDS there. These are the two software to do a thermal sizing of a heat exchanger. All the rules of Kern is inbuilt here. And another important process equipment is a column, distillation column, where you have a heat and mass transfer. Reactor, we cannot do it as it has a catalyst. So we don't need a catalyst information, and it's all patent. So we cannot do a research over there. We can purchase that, but column we can do. This is a open art. There is some relative volatility and efficiencies. The softwares of ICs are provided with these chemical natures. Whenever we provide what is the inlet we are providing and what is the product purity we wanted to separate, then the ICs will tell us what is the reflux ratio, what is the number of trace, what is the minimum trace, where is the feed has to go. ICs will tell us. And we have a KG, TAWA and Sulcol. These softwares are used to size the equipment. What is the diameter of the column? What is the height of the column? ICS is the one which tells how many trays we need, whether the performance of the column is met or not met. So I recommend you guys to get exposed or learn Aspen ICS, HTRI. These two softwares, if you are familiarized at least, and if you know the significance, you can get into a process design field. And other equipments or major equipments are vessels, pumps, and we need to do a single phase line sizes. These line sizes are mostly done by engineering contractor, design spreadsheets. Every engineering contractor is having a design spreadsheets. It's a Excel, it's a patented Excels. People use it and we can size it, no problem. In a process plant, the costly items are reactor, columns, heat exchangers, vessels, pumps, then lines. So people will focus on lines. If you are able to reduce the line size, then we are providing a economical plant. So people give importance on the line sizes also. And very interesting we have it is two-phase lines. It's a really a very nice field. There are engineers called flow assurance engineers. You would have heard somewhere. Flow assurance engineers is a hi-fi job and hi-fi nature also. We can predict how the single phase will behave, but it's not easy to predict how the two phase will behave. That too in a kilometers of pipeline. The recent project in a worldwide speaking project is China project. They were going to make some pipeline project between Europe to China, Russia to China, Arctic continent to China. So these pipelines are very important when compared to vessels. When we make a 30-inch of pipeline for a kilometer, then it will be bigger than a process vessel. And the problem is these pipelines will cross domestic area, commercial area, forest, rivers. So when these all territories are involved, it's a very nice design to get into this. After my webinar, people can Google it, what's Volga is doing. Why this pipeline engineering is very good. What they are doing it just to get in exposure. And we have a pipe sim. This is for easier one, but Volga, it can do a very good, nice, I don't know how to express. If you have a knowledge on the pipeline, then you will, you can feel and then you can appreciate. I would like to share one example. If you have a well in the offshore and our facilities in the onshore, the well will have crude oil, water, gas condensates, and salts, and some sands also. This Volga will predict what will happen, whether we will get oil or not, or water and oil will get mixed and create an emulsion. It's a very nice software. And we have some transient softwares also. Volga will do, PipeSim will do, and then PipeNet will do. These pipeline transients are nothing but if you have a kilometers of line and it's closed, suddenly somebody closed or some fire happened and the receiving plant is closing, what will happen to the total pipeline? This pipeline may rupture. Suddenly the pressure will get increased and it's very fast. It can happen in seconds. So these softwares will study what will happen in case of some emergency. Somebody is disturbing the normal process, it will tell. And we have a beautiful design flare. If you guys go to any process plant, I recommend you to visit on the floor design. It is not a normal pipeline. This all process plants will have a pipeline, but flare line in which we have adiabatic process. Other lines are isothermal process. The temperature and pressure of the line remains same in a process plant except the flare line. So we have a dedicated software, flare network, Aspen FlareNet for a flare network design. And again, we have a dynamics. Dynamic software is also there. If you have a compressor and it goes to surge, what will happen to the compressor? Or somebody by mistakenly close the compressor discharge. We don't design for that, but happened. what will happen to the compressor? Compressors are costlier items, and it can create a very big damage. It creates a pressure. So we do a dynamic analysis. Even somebody close, what will happen? We will design for that. So Aspen ICs has another version, Dynamics. It's very good software. And for energy optimization in refinery, we have a Aspen Pinch. In refinery, as well as we can do it in any plant where we are heating it. One side we will heat, other side we will cool, because the raw material needs a heating and the products needs a cooling. So there is a energy optimization. Aspen Pinch will do that. And some dispersion studies are there. Okay, recently in Vizag, there was some leakage from the process plant. They stored and something went and leaked. How we need to predict how long it will affect. That's why the process plants are little far from the industrial and residential areas. Residential areas, not from the industrial area. It's from the residential areas. How far? So these the dispersion study, we need to do it. So as well as flare also, there are some plants right now. The flares are designed for normally no flow. It should not burn in normal operations. We need to recover any relief. But still there are plants which built 20, 30 years before. These plants are now upgraded using the software. They are increasing the flare stack. Okay, our dispersion is very high. If you visit Manali, you can smell the chemical leaks. It's happening from flare as well as some cooling towers. So now people are conscious on the environment, and people are started living near industrial areas. So FlareSim is another software used for dispersion studies. These environmental team will verify it. They will monitor it during the design phase. They will verify it. In normal operation, they will monitor it, and then they will control the population near the industrial area. These are managed by safety team. Okay, next, coming back to codes and standards. So in any project, we have set of rules and regulations to do any design. We cannot do anything, as I say, we cannot do anything new. Nobody will accept. No client accepts. We have a set of rules. Okay, this equipment, it should be designed like this only. So these are called codes and standards. Normally, any equipment will be designed as per ASME, also American Society of Mechanical Engineers. Though we are process engineers, the mechanical also vital role once we implement. We can say what will be the diameter of the vessel, height of the vessel, pump specification, but finally it's a mechanical one. Finally, we are going to see as a mechanical item, which is rotating or separating. The performance is a chemical performance, but the appearance is mechanical. So there are rules. It's set. Once a process engineer gives us sizing and design conditions, then the mechanical engineers follow these rules. As well as whenever we size also, we should be aware what's given in ASME. We cannot give something new to a mechanical engineer, then they will come back. We cannot purchase this one in the market. For heat exchangers, we use tubular exchange TEMA. There are rules, how many tubes has to be set, how the arrangement has to be. These codes and standards are basically for construction, how to construct. While designing, we may not need this, but how to construct. For a process engineer, heat exchanger is simpler. We can say, okay, this must be the duty of the exchanger, this must be the inlet, this must be the outlet, and this must be the pressure loss across the heat exchanger. But to meet this all, we need a mechanical item. That's a design. That mechanical item has set of rules and regulations to manufacture it. So TIMA will tell us what will be the standard tube length, what will be the standard tube ID. So whenever we design size or dimension any process item, then we need to apply these codes and standards. And API is American Petroleum Institute. I recommend you guys to get familiarized all this when you read on process equipment design. So we need to apply these codes. These codes, API, without any API, you cannot purchase any equipment outside the market or plant in or place inside the plant. Simply, I will give you one example. We have a pumps in our house. These pumps are non-API pumps. There is no guarantee on performance. Even somebody close the pump, we can run the pump for an hour, but in process plant, we cannot do that. So every equipment, that's why I have not listed API numbers. API code is available for all equipments. And specifically for columns and absorption towers, we have a Fractionation Research Institute from France. They have set the rules. What will be the column flooding? And for a safety system, okay, again, the process engineering is having a safety design engineers. They do this fire water system as well as equipment protections. They have a set of rules. They will be following NFPA. The fire water pump should be designed as per NFPA, not as per API, because this is falling under the safety system. The reliability of the fire water pump will be much higher than the API pump. And we have oil industry safety directorate, that is the Indian regulations. You can read. In fact, in OSID is giving very nice update, and whenever some incidents happens inside the India, they are studying it, and the studies are posted here. What went wrong, they are posting it, and it's a mandate to incorporate in the new or upcoming projects the lessons learned. So when we come into a design, if somebody wants to put a plant, we cannot give a design directly. First, it has to go to a feasibility study. We need to do a conceptual design, flow scheme. What is the flow scheme we are going to select? Licensor we need to select. If it is an oil and gas project, no need to have a licensor. Engineering contractor can finalize the configuration. He will make a block flow diagram, and then he will apply for environmental clearance. Once it has come, then it will go for a basic design where the flow scheme, heat and material balance, plot space, equipment sizing we need to do for a preliminary cost. This project will cost this much. So basic design, till this time the equipments are not sized. They will give a approximate sizing. Yeah, this is a feed phase where the full of chemical engineering is applied. I can say process engineering is applied. Now the project has been cleared for environment, plot space is fixed. They want to finalize the design. So in this phase, they will finalize what are the codes and standards to be used. If it is in India, what is the standard to be used? In fact, if you read the codes and standards, we have it in international level, Indian level, and then district wise. So they will set up in field phase what are the codes to be used, and flow scheme will be finalized, performance guarantee will finalize, equipment dimensions they will finalize, line size, relief system, safeguarding system, everything will be finalized, and they will go to a market, and then they will get one quotation from vendor also, whether we can purchase this equipment in a market or not. We are not providing any abnormal or non-standard design. They'll check. And in the during detail engineering, so the feed phase is a important phase. Any process engineer would like to work in that. In the detail engineering phase, it's only a construction and finalization of some utility systems, relief system, operating manuals, constructions, support we need to provide, go for a commissioning, and performance guarantee we need to do that. So the important design is happening in feed. Okay. I will take one typical gas dehydration and compression system. I will take you to one of the very good software, ISIS. I think St. Peter's is having some ISIS software. I recommend you people to go and get practiced and write in your resume familiarized with ISIS. So this is one of the very good, nice software you are seeing it here. I'm having the latest version here. So this is one of the scheme. So we have a gas production from the gathering. Before that, we will have a lot of wells, pipelines, and it comes to our process plant. This is a process plant, one of the gas compression and dehydration. I'm trying to fit here. Okay. So the upstream is another facility where there is a wells and kilometers of pipeline will be in the upstream. So this is a process plant. Here we are gathering all the production fluids. I can say it's a production. It will have water. I can show you. So this is the stream. In this we have a vapor, we have a liquid, and we have aqueous phase, water. So when we do a chemical engineering, we may have these three fluids. How do we know density of the mixed fluid? How do we know the viscosity of the mixed fluid? This software will has a full backup and data. These are reliable softwares. If we do design in this one and implement, it will perform. It has a pilot plant data also. Maybe I can give some introduction about this software. So this is a simulation and modeling software. We can simulate any fluid here, but this software has some limitations. Okay, I will start from the first. Okay, whenever we start some equipment design, this software we start with ISIS. We need to make a process scheme that is called process flow diagram and make heat and material balance of the total production plant. So I will open you one. So in this case, okay, I want to start a plant modeling. I will open with, okay, I will open a new one. So okay, so once I start here, this is a new environment. First, simply I will take some water is there. I wanted to boil it. How much heat I need to provide, I need to calculate. When we do by theory, it may take an hour, but when we do it with this software, it can happen in a minutes. I will tell you. Once we open, it will ask what is the component, chemical component we have. If you see here, from methane, you see here, all chemicals are here. All chemicals, and with the properties. It has a full set of the properties. Okay, let me select easier one, water. Then it will ask. This is one of the thermodynamics we use. You can appreciate what the software is doing here. You see, we have packages. We say Ping Robinson in our college we study. SRK. All the equations are inbuilt here. Some equations are not in the software. As I say, this software is not very good for electrolytes, but still it will do it. You see, glycol is another one of the electrolyte, but we don't choose this in the software. We have a specific software for that. So again, if now I have chosen water, water is, for a water, Ping Robinson is not a good tool. We need to have a steam. So here there is a steam calculation packages here. If I say, okay, mistakenly I select this one. Okay, so these are compactable, so it is saying green. But if I say something wrong, yeah, this is not incompatible. So this software will direct you if you do a very big blunder. So I can choose ASME Steam here. Then I go to a simulation. Now I have chosen component and thermodynamic package. Again, if ASME Steam I have chosen, so it is not asking any properties. But if I select Ping Robinson, it will ask again, what is the enthalpy equation I have to use here? What is the density equation I have to use? What is a modified critical pressure, critical temperature estimate method, and what is the viscosity estimation methods? And what is a method to estimate the thermal conductivity? This plays a thermal conductivity plays a role on heat exchanger sizing. And what is surface tension method? Surface tension plays a significant role in separation. Okay, so this area is really, if somebody is good or want to learn thermodynamics, practice this software. This is full of equations. I have not explored much because we use oil and gas chemicals. Sometime when we go to fertilizer, they have very recently updated fertilizer. Some packages they updated for ammonia. It behaves differently when compared to another oil and gas chemicals. And good thing is that we cannot model seawater here. There are some exceptions. Okay, and when we go to a crude oil, I don't want to cover it, it's a big topic. When we go into a crude oil is not a single component, it's an array. Based on the boiling point, the composition varies. We can model a crude oil here, but I'm not covering here. If you go through here, you would have read the Watson K factor in our theory books. It has a significance and the provisions are here. The software covers all. And for reactions we cannot model. As I was saying, the catalyst property is very important. We cannot model reactors, but still we can model a reactor. Simple reactor, it's a combustion. Combustion is another reaction. Combustion we can do it. Combustion don't need any catalyst. You can make a note of this. Combustion don't need any catalyst, and it's an open out reaction. These are some on the software of this. And when we go into a simulation, yeah, now our environment of modeling started. So I want to heat up the water and make 1% boiling. So this is a water and I want to heat. Okay. These are the software navigations you can learn by referring the tutorials. You can check in Google. I'm just giving an eye-opening on this software. So once you open this one, it will ask, okay, software don't know what is this. They have to tell. This is composition. Here water, so I give mole fraction 1. If you have a real composition of oil, water, we can provide. So then it is asking the initial conditions we need to provide. What is the temperature here? What is the pressure here? So I give here 60 degree. And I make it, it's a hot water. So the vapor fraction is 0. Then the software has calculated what will be the pressure here. 140, the liquid will be, it's PSI, okay? It's absolute. So in reality, if you read in gauge, it's a 17 PSI, around 14.7 plus we need to add. So in the outlet, I need to have 1% vaporization. And pressure loss, this exchanger is a mechanical component which will create a pressure loss. So I'm giving 1 PSI. I think this needs energy heating stream also. Yeah. Now we need to define what is the flow. The software needs the initial conditions. So we have provided it is a water and it's a 140-degree hot water. In order to save water, we need to provide a vapor fraction. So then we will give 1000 kg. And this software is having all units. If you read this now, it has full property. We don't need to go to a Moliere chart. It has a full property. What is the water molecular weight we know. Now what is the density of the component? What is the volumetric flow? What is the viscosity? Full nature. This is a full chemical property of a physical as well as chemical property of a stream. So we can get it from here. No need to go anywhere. Don't need to check anything in Perry or Moliere chart. Simpler we can get it. Even it's for water, okay, we need to go to Moliere chart, refer to graphs or tables. Here nothing. It will give a straight away answer. Whenever we change, it will give straight away answer. And now it has estimated what is the duty. This is the duty of a heat exchanger. To vaporize 0.1% of vapor fraction of water, I need this much kilowatts. We can change the unit also. So we can represent here what is a BTU. Normally MMBTU will say to quantify the exchanges 0.2 million metric BTU power. So now this some examples I'm giving on this software. And then the software is having many modules. We can do, as I say, energy analysis. We can do safety analysis. We can do dynamics here. We have a blowdown and depressurization. This is one of the very good engineering where you can apply isobaric, isogoric processes. It is depressurization is one of the isogoric processes. The volume of the process remains same, but we will change the pressure from high pressure to flat pressure. So this is a very good tool. But I recommend you guys to learn how to model a smaller stream. Okay, how to open this, how to set up the simulation environment. Then you can build a complex processes. Okay, this is about this IC software. I'll go to our simulation. So in this case, we have made some set of process scheme. We need to size now the major equipments. First, they do a compressor. This is a long lead item. Columns they do. Then they do vessels. Then they do line size. Then pump. Like this, it will be get progressed. Heat exchanger also they will do it along with the vessels. So the scheme is finalized here. I don't want to go into the simulation. It is another big topic, modeling and making a conceptual design, whether I need a compressor or not, whether I need a heat exchanger or not, whether I need a vessel or not. These are all again a conceptual. I would like to cover only few equipment sizing. Okay. So maybe we will be running out of time, but I will cover some equipments. Let's start with the line size. So I want to size what is the line size. There is of equation, Darcy's equations. It's a universal. It's not going to change. Instead of going into Excels, we can do it here. There is a pipeline segment. Do this one. So I want to size what will be the pipe size for the process feed stream. And this is a two-phase stream. Okay. So from the plot plan is a drawing in which we see where the equipments are located and what will be the relative elevations and relative locations. So I assume this pipe segment between the inlet, from this inlet to this valve, here we have a pressure loss. So from this one to this, I find it's 100 meters. So I installed a pipe segment here. I go to a rating and I add a segment. This is a pipe, equivalent length is 100 meter. And then elevation change, I don't provide now. Okay, so in the preliminarily, we need to select what will be the line size. We can, by engineering judgment, we know, okay, this much flow is going, so it could be a fine like that. So we select some 20 or 16 inch, and it will ask whether the heat transfer is in the exchange in the pipe or not. Normally the process plant pipes are insulated and no insulation. Let us give this stream, we will copy this stream to 6. Open this, go to process feed. It's done. Now it's the line size is done. Whenever we see blue and this gray, it's done. Otherwise it will show red. So let us see what is the size we got here. So we have given a 16-inch line, and then it's a OD. ID will be a 15-inch. We are seeing here. Okay. Okay, again, this as a provision to flow assurance, we can verify is there any corrosion, erosion, hydrates. I think you read the two-phase for slug also. Is there any wax deposit? Everything it will find. Before going, I want to show the results here. I want to see velocity. Normally we use velocity. So liquid velocity we will select. Each segment we can find. Let's make it this one. Okay, inlet velocity, vapor velocity, pressure loss. Okay, this is fine. In fact, 16 inch is very big for this. The velocity is very low and pressure loss is not much. So we can reduce this one. Yeah, again, the pressure loss is a little big. So we need to increase. It's an iterative process. Okay. So the inlet vapor velocity is 87 feet is fine. Liquid velocity 5 is fine. We have a set of rules here. Maybe I can show some. So these are the criterias. Okay, we have to select, is it a gas? Yes. Then is it a compressor suction? Or again, gas is having a general gas, compressor discharge. So we need to filter it one by one. I say, for example, gas, and it's a gas suction, compressor suction. Then what is the criteria I have it? I don't have any criteria on pressure, inlet pressure, and I don't have any criteria on velocity, and I have only a criteria on rho v square. Rho v square is a loss. It's a noise kind of vibration, and we have a pressure loss. So per kilometer, we should not lose 0.7. So we will iterate the line sizes here. We will iterate the line sizes here to meet this requirement. As well as we have direct spreadsheets. So I don't want to go inside. This is a detailed engineering Excels. If we copy the inlet and outlet inlet conditions of these properties, we need to provide the line sizing properties, flow, molecular weight, compressibility, viscosity, density, and Cp by Cv. If we provide this, these are used in Darcy's equation. Same we need to provide here. Then it will say we can directly iterate here 3 inch. This input again 3 inch, 4 inch, 6 inch. We will verify for 3 sizes. In that optimum we will select. The same I was doing here in a HYSYS. So we need to meet this criteria. We will change the line size and then finalize it. This for line, and we can go to a drum. The purpose of any drums is to separate vapor and liquid and hold the liquid for some time to manage any process of set. For example, let's take this is a compressor. So here the compressor per inlet knockout drum in our scheme is to separate any liquid from the vapor, and the vapor only will be going to a compressor. If there is any liquid going to a compressor, it will damage it. So we need to remove the liquid. Yeah, I find small liquids are here. So we can size this one. The system is converged. In HYSYS itself, there is methods. Preliminary size, we can do it. Okay. So the system is converged. Now I need to have a preliminary sizing. So I open and put this a vertical vessel, and the cylinder, it's a disc they are asking. Normally it's a hemispherical. So now if I say quick size, it has done. But the formula behind this one is, I will explain you in one Excel. The formula behind this one is Stokes law. Any vapor and liquid, if you put it into the vessel, by density, the liquid is getting separated from the vapor. So there is a formula. That formula is Stokes law. So here it uses the Stokes law. If you provide vapor flow and the density of the vapor and the density of the liquid and flow, these are the major inputs used in the Stokes law. It calculates the velocity at which the liquid can separate from the water, from the vapor. So when we provide some flow here, okay, I'm providing something here. The vapor density I make 25, and liquid I make water 1000. Okay, then if you see here, it has calculated the critical velocity. There is a Stokes law. From the Stokes law, it calculates. Apart from this, a process equipment, what is a dish and we have it? We have a spherical, whether there is a mesh or not. If you read design books, there is a mesh to remove, to fine tune the vapor liquid separations. So I say here, I don't have any mesh. And what is the service of the fluid? These are all engineering designers confidence and their design practice. For me, it is a compressor knockout drum. So I will select 3. Then here it says for the compressor knockout drums, the critical velocity percentage should be 80%. We should not go behind that. It gives directions to us. Okay, select 80%. I do say 80. And what is feed diameter? It's an inlet nozzle. This is to make a height. So I make 6 inch. Okay, this is the alarm. I don't know how many of you understand this. This is alarm. Just I give 1 minute before, because these are the time allowance for handling any disturbance. Okay, I have a pump here. Somebody tripped this pump, or the pump by mechanically, the pump has some interlocks, and the pump feels it's not in good. Say then the interlock will start say, okay, this pump is not working, and it has some trouble. It will go for shutdown. Once this close, what will happen to compressor? The operator will get a acknowledgement, get an alarm. Something went wrong. Somebody has to go and fix it. This is a 1 minute time. So these are the allowance we make it 1 minute, 3 minutes. It's based on the plant. There are automatic plants are there. If we go offshore, it's automatic. They don't want to have a manned platforms. So they will make more allowance for that. So this is the allowance, just knowledge. And we have a set of rules to select it. There is no big chemical engineering beyond this. There is only operating philosophy. Then once I give this, I have sized my vessel. See, it has calculated the minimum diameter. And it has calculated the allowances for the each and every high levels. And this is my column height. Vessel height 2.4 meter, and the diameter is minimum 0.8. We need to round off 0.8, but the engineering designers will make bigger by providing a over design factor. We need to provide here. We will add the margins here. Instead of giving 1000 from the HMB, we will take the flow, and then we will make it is simpler. Even if I copy these inlet properties, I have given some rough values, but in reality, real values also we can provide. These are the flows, mass flows, vapor flow, liquid flow, and the property we can get it only the density, mass densities. Finish. Here my Excel and the ISIS units are different, so I don't want to touch. So I have given a rough values. This is for a vessel. And the beautiful process engineering equipment is a column. I just want to cover one column. And for the pumps, it's very simpler from the software. Now the pump suction pressure is there, discharge pressure is here. Once we converge this, if you take a knockout drum pump, discharge pump, so the inlet condition is this. Pressure will be 20.25, but we will make some allowance for piping losses. there will be some pipe between these. So we'll make some assumption when we make a purchase specification. And discharge pressure is there. If you have any control valves, all the fittings we need to add, then we will get what is the discharge pressure. Pumps are simpler, but it needs more detailed hydraulics. During initial design we don't do, but during detailed design they will add a lot of piping components. They do a dedicated Excel. We will appoint some juniors. Normally hydraulics are done by juniors. We will appoint some juniors. They will be doing hydraulics because it needs full of effort, follow up of data. So we will go to one column. How do we size? So we have here we have a dehydration process. We are going to remove water here. In this we have a dehydrator here and the regenerator here. I add regenerator here, which has a typical system. This is only a absorber, but this is a typical system. I would like to cover this one. Let's take this column. It is get converged. Okay, now I need to size what will be the column, and in eye level, we need to find how many trays we need. Okay, normally these services, absorber and regenerators using a TEG are typical because the nature of the TEG and the gas mostly remain same. We are going to remove water using the TEG. So water is fixed, TEG is fixed. So normally in an industrial practice, we will have how many trays? 3 trays. These are all ideal trays, theoretical trays. I can say ideal stages, theoretical stages, but it will have some efficiency, 70%, 60%. These are all rules we need to follow, or from the experiencing plant they'll say, okay, for this water separation, this much purity of water removal, we are having a problem with this much trace. In future we need to increase the number of trace more. So this is the column monitoring. Here when we converge, the reflux value is given here, and the condensate temperature, reboiler temperature. Reboiler temperature is fixed by the heating medium, and the condenser temperature is fixed by cooling medium. We cannot cool more than the coolant. We cannot heat more than the heating medium. So these two are fixed. Reflux ratio is by operating plant. We can also find, I will tell you, here there is one shortcut column. Yeah, if you place this one and give properties, it will converge. It will tell us how many columns we need. I will just show you here. So if you provide the parameters and the specs, we need to provide what is a key component. That is a separation we need to define here. And the operating pressures we need to define here. External reflux, we can give estimate value. Then it will tell what is the minimum reflux is required. We give iteration, but it will tell us how much. It's a guideline. Then we can make a main column. So now the number of, how to make a number of trace reflux is by shortcut columns. Use HYSYS shortcut columns. What we're doing in our college is finding a equilibrium curve, then number of stages based on the purity. Here nothing is required. Same, but it will calculate the number of trays by providing the key parameters. We have to define what is the key component and what is the our expectation and the performance. Once we do, it will calculate the equilibrium curves, number of stages. If you see here, it is saying the minimum number of trays, actual number of trays, optimum feed stage, condenser temperature, reboiler temperatures. And in a column, we will have a rectifying section and stripping section. Everything it will tell you. What is the reboiler duty? What is the condenser duty? It will give. So by using this, you can find the number of stages. Then we need to size what is the diameter of what could be the diameter of the column, what could be the diameter height of the column. So there is a column environment here. If you go inside, okay, I think they have fixed everything here, diameter also. Yep, this is 3-stage. So 3-stage, they have done it. Okay. Okay. So here, yeah, this is a column sizing now. So I have a 3 stages only, theoretical stage. So I want to have sizing now. So I say auto section, because you would have seen in the process plants, the column bottom will be very big, top will be very small, because it has a 2 sections. In this, we have only 1 section. When we give auto section, the software will tell us what will be the section, minimum section required. It is saying only 1 section, and the expected diameter will be 0.8 feet. It's a very small column, in fact. I don't find it, so why it's like this. Let us see this. Maybe the criteria is what they have set may be wrong. Okay. So here, again, there is a system factor and the over design capacity. Those things they have not provided, in fact. If you provide here, we can find a column. You close this column. It's a packed column, little complex. This. You'll go to a tray column. Yeah. So here it's a tray column. It is having only 1 section, and it's a trade. We can change all the internals: bubble cap tray, sieve tray, or valve tray. If we go to valve tray, we have to tell us to the software what kind of valve we are choosing it. So normally we do with generic bubble cap. Then we need to set the rules for the sizing. So this is the tray sizing environment. We can select what will be the tray type, number of passes. You may be knowing, I hope, there is a number of passes on the column. This is a single pass. If we make it 2 pass, you see this one, the center down, the downcomers are in center. So it's like this. 3 pass is not there. 4 pass. 3 pass is there, but we don't use it. So even passes are good. So 4 passes here. So we can select this one. And also the software will tell us how many passes required. So we'll give conditions. These are the conditions we need to provide. As I say, over design limit we need to provide. Its over design factor is 1. Normally it's 25 columns are designed to 125%. So system factor, foaming factor, I don't know whether these values are in the syllabus or not. This we need to use is based on the nature of the chemical. Amines will foam. During the separations, amines will foam. So we need to have a 0.8 here. It is inefficiency. And what is the pressure loss across each tray? What is a jet flood? Normally we use for a new columns, it should be 80%. And the backup, we are loading, it's normally 2 to 8. We will not go behind that. Here it's given bigger, but we'll go inch. It's in inch, we'll go 2 to 8 inch, maybe 8 inch. 8 is 98. It's 157 is given, but we'll go 98. It's a new design. These are again the project specifications we use. So once we give all this, then the results will come. Number of passes 1, tray spacing we provide. It's a standard, and section diameter, a height, 16 feet height. 0.4 feet is wrong here. Wrong. It's in half an inch. It's not half a feet. No. Half a feet is not a correct one. And it will give a error. What are the design errors we have it? We need to handle. That's why this is, you see this is less than the minimum diameter of 2 feet recommended by columns. Consider using packed column. It is saying the column is very small. Consider, we need to troubleshoot one by one. Okay, so with this, I will complete my presentation now. And any queries, please.
Any queries? We can post in the chat box.
Okay. How do I read the chat books here?
Sir, is Aspen HYSYS is the top end of the programming sector, or is there any advanced feature of this Aspen HYSYS, sir?
Advanced, we don't have advanced as of now. Aspen HYSYS is the best software used internationally for the simulation and equipment sizings.
So your views on open source software like DWSIM a substitute for Aspen? Rohit Kumar has asked.
Sorry, there is some breakage. Can you repeat?
Yeah. Your views on open source software like DWSIM as substitute for Aspen?
Yeah, DVT sim is there, I think. ProSim is also there. We can say substitute, but the industry is using HYSYS. Again, it's if we read in a high level, what is the difference between these two softwares? Only the environment, the equations, database remain same. Only the difference is the environment and some tuning. I was saying there is a Promax software for simulation, which is very good for electrolytes, because Promax is having a very good database, plot plant, pilot plots, So the Promax is used for electrolytes. IC is having, but again, it's a confidence of the licensor and engineering contractor. Nothing more than that. The equations and the formulas remain same.
Okay, another question. Sir, can we use SAS software for process design?
Yes, yeah, yes.
Yes, software.
Expansion, I have never come across
Mr. Wasim Akram, can you explain it? SAS software. They have asked in this SAS software.
No, they have not come across SAS.
Any other queries?
Maybe those are all at study level or literature level, but in industry, no, SAS is not used for process design.
They're asking again. Actually, can we use DWSIM software?
Yeah, yeah, we can. Again, TW is it's for amines. Right? It's amines. We can use that for amines. T switch, they say T switch. It is for amine recovery, sulfur recovery, we can use that. And in ICs also, we have some packages supporting ICs, supporting some packages supporting amines are there. We have it here.
Another question.
Yeah.
Do you have any idea about fluid flow software?
Yeah, that is Volga. Yeah. It's for a pipeline. We can use Volga.
So next question is that what are the documents and details we get from the customer, and the and details need to give to the customer from design engineer?
Yeah, it's a very good question in fact. So again, if the client, our client, he comes with a problem or he comes with a new idea. So client will come with two options. One is new idea or problem. There is a existing plant and it is not performing well, maybe by quality or quantity. Quantity means the production is not to the point, or they want to increase the production. So they will come up with the problems, or they will come up, yeah, we have a money, we are going to build up, and government is planning to increase. For example, last year we put a ammonia urea plant. Government is planning to increase their urea production in India. So some clients are coming, yeah, we wanted to increase, and please tell us what is the technology we can select and how much it will cost to put up the this fertilizer plant, and when can we commission, how long it will take, like that. They will give all the documents related to a land environment to us. We will give complete design, what is the technology, how it will operate, from the technology to finally how it will be operated, operating manual. From design, from process side, we need to give the design specification of the equipments and heat and material balances, how to operate. Then it's a big team is there, mechanical is there. They will purchase based on the process. They will purchase the equipment, construct, commission, full service we need to provide. I can say lot of documents we need to provide them. Lot.
Next is that, next question. On what ways Aspen is better than other simulation softwares? Because industry started to use their own softwares based on the requirements. Like Honeywell started to use Unisim. So why Aspen is unique?
In fact, Aspen is internationally used, well-known software. Unisim is also good software. As I say, the physics and the chemistry and the database principle remain same. Only the difference environment and their practices. But if you say Unisim, I know Unisim. Yeah, people will say, okay, he knows simulation. But if you say ISIS, yeah, he knows better. This is used in range of process engineering. UOP may be using for refinery. They may not use for oil and gas. They are not in the field of oil and gas. They are not making any platforms, but they make refinery. But when we want to make platform, yeah, ISIS is required. If you start with the ISIS, then we can go into any simulation software. And again, one more, UOP, why they are preferring their own software? Because they have their own pilot plants. They have the models of reactors and catalysts in their software. Maybe ISIS is not having that. ISIS is not having any data of any catalyst. It's a open, but they will have it. If we go to, there is a company called Schlumberger. They are in oil and gas. They have a membrane separation technology also. That is not in ISIS. So they use their own software, which is proprietary. So in this way, ISIS is good for beginners to start with a simulation. Then when we want to go into a specific one, use the proprietary software from the licensed person.
Okay. Another question is that, can we use Aspen software for three-phase fluidization concepts? Three-phase fluidization concepts.
No. No. If you say reactor or any fluidized bed reactors, no, this will not do it. These are a proprietary design, in fact.
Okay. Another question. The equipment designing, which standard should we use for PSV and control valve sizing?
Yeah, PSV, it is 521, API 521 and 520. Use that. And for a control valves, from process, no standard. We will give what is the inlet pressure, what is the outlet pressure. Then there are instrument standards to make it. We don't do any control valve size. We'll just give, this is my scheme. I will supply this much pressure and I need this much pressure out. That's it. In one page we will give here.
Okay. Another question is that actually during simulation, the conditions we give will be exactly as real-time operation.
Yep. It will be exact, correct, and accurate.
Okay, next question. Which are the good platforms to learn Aspen HYSYS?
Good platform for college students, start from your university and college, or go to an internship. It's very difficult. It's very difficult to get an internship with any design companies because they will be busy and these are all costly softwares. So they will not give a training on this. It's good platform for the beginners is start from college or university and make your project using this software. Then you will be a real-time you'll be exposed to a real-time designing.
Okay. Next question is that when we use Promax, mostly we use Aspen. When can we use Promax?
Yeah, it's for amine service, tech columns, sulfur-based sulfur recovery units, electrolytes. If you have a salt-based chemicals, so that time we need to use Promax.
Another question, that we don't use any standard for control valve sizing. Okay, you said that we don't use any standard for control valve sizing.
Yeah.
Then for what ISA 7510101 used for?
Yeah, ISA, as I say, from process we'll give inlet and outlet. ISA is for is from instrumentation. They use that. They use that. ISA
Any other
is
queries?
and also I would like to add. So when we do a process engineering, we have a limitation. We, as a process engineer, we can do a civil design also. We can give civil loading for the foundation estimate. We can tell I need emergency power for this pump also. So we are the one leading the EPC company. We give them the directions. I need this, you get this. So they will make it, because finally the process plant has to operate. So even for control valves also, yeah, we say, yeah, we need a control valve. This is the flow, this is the pressure loss, and this is the property nature. Then they have their own standards, they will come up. In vessel, we give ID, design pressure, design temperature, height or length, it's horizontal, vertical. Then the mechanical engineer finds what is the thickness. We need a thickness, but we don't do. We have a mechanical engineer, he will find. So there are lots of standards in EPC, but process is limited and we need to do at eye level. Okay.
Next question, there is any standard for line sizing?
Yeah, we have, it's a Darcy's equations, and I will show you. Every company is having their own criteria. It's a matter of do you want to have a bigger pump or bigger line? So every company is having their own standards. So we use the industrial practice. And for offshore lines, yes, we have a FAI 14E. It says for offshore and flow lines, there is a flow line called flow line. They say it's not a pipe or it's not a pipeline. It's a flow line. We have a APA 14E.
Okay. On behalf of students, so to get into a process engineer, what type of, how they can prepare themselves when they are completing their final year? So what they have to learn and what topics they have to concentrate to prepare themselves for a process engineer or for a design company?
Yeah. First, understand how each and every, by equipment we need to understand how the each and every equipment is operating, what it is doing, and how it is specified. Basically, the design engineers are doing specification. Okay, I need a compressor, and what will be the discharge pressure? What will be the suction pressure? So when we go into a market, we need to purchase. So this, our view should be always by equipment. Yeah, this equipment is doing this. We need to calculate and specify this parameter or a number, so we can size or we can get this. So we need to think of that way. And when we go into any site visit, we need to think by equipment. because the schemes are fixed at high level. So as a chemical engineer, you cannot change or update any schemes or process schemes. But get into a process design, equipment, we need to think, yeah, column is doing this, and we need to size this much only we need to size. This is only to be generated. That's it. This we need to do, and we need to get into a lot of site visits and how the plants are operating. Because once we know how the plants are operating, then we can do sizing. This what, whenever we go site, get you into deep knowledge. What is this equipment? What it is doing? How it is sized or how it is purchased. In our house also, when we construct a house, we are purchasing a pump, borehole pump. We are saying this much depth and this much top it has to go, and power should be this much. This is the specification of that pump. Same way, whenever we see some process equipment, we need to see, okay, what are the conditions to be or parameters to be specified to get that equipment. That way we need to think. This is a design. And get the software knowledge. Get the software knowledge. And whenever you do your projects, try to use any one of the software. Every industry is looking for that. Yeah, do you do this one? Or have you having this knowledge? Like that. We need to think of simulation and modeling. This is the plant, how it is transferred into a computer. That's it. So improve your software skills, get into the knowledge of plant operation, and then implement in the software. And if somebody going to site, you get some data from sampling, and if you have a software, same data you try in the software, whether are you getting the same viscosity or same properties. If you done that, you got it in the right direction. Finally, when I do design here, all are trusting, okay, we are generating a good data for sizing and it is working. I'm saying do it in the reverse. You get the data, try in software. And some design agencies are there outside. I don't know how they are successful. Maybe for the persons who are already in a job or already in operations field, may be useful. For the students, start with your university or college. And some now the communication is very good. You can get some softwares online also. Try with YouTubes. Try some tutorials. Model some plants. When you go to site visit or project, collect the plant data. Try in softwares. Then it will be a good one. And whenever you go attend any interview, you will be very confident when you are answering it. Yeah, this is what I can recommend.
Next question is that difference between FO and RO when we design orifice and which standard we use for.
Yeah, for process, I was sharing your detailed engineering design. This is part of detailed engineering design. FO, RO, for us, flow we need to restrict. Okay. We have a certain flow. We want to start both the same terminology. Maybe instrument is having some differences when they do that. But as a process engineer, for us, we need to restrict the flow. That's it. We will place a restriction orifice to reduce the flow, and we will give inlet and outlet pressure. They will come up with some kind of a washer like that. For me, at university or college level, you can focus more when compared to this. These are all detailing.
What is the difference? What is the difference between PSV and PRV?
Yeah. Okay, PSV, pressure safety valve, and TRV or TSV or thermal safety valves. Pressure relief valves are meant for process. There is upset and the reliefs are opening. But TRV, okay, some piping segments are blocked and some heat ingress is happening. Maybe it's a solar radiation, or unfortunately process is closed. Somebody opened the heating medium, so it's getting heated. So then the thermal valve will open. It is only meant for thermal relief due to the fluid expansion. But the PSV or PZV, they say, PS safety valve is for any process upset. But thermal is only abnormal heat input.
Another question is that if I want to become a design engineer, what standards and codes I need to know on my fingertips?
Yeah, first you need to know what is API, what is ASME, where it is used. That's it. Familiarization of codes and standards enough. Because as I say, all codes and standards are inbuilt here. If I open here, the principles are set here. It is saying how much velocity I can have it. Right? Principles are set here. Where to get those principles? That's enough. Okay, I have a API for pressure safety valve. I need to follow API 521 and 520. Finish. Familiarization is enough. We don't need to go know in detail. If you know, okay, this standard is giving this one, I will refer and then I will implement in design, because every year the codes are getting updated. Not by every year, but periodically it's get updated. So no need to memorize the codes. We need to memorize only the code number.
Any other queries from your side? Participants, any other queries? When we use water as a feed for line sizing, which equation we should use to simulate that feed in a facility? Repeat the question. When we use water as a feed for line sizing, which equation we should use to simulate that feed in a facility?
Yeah, it's a steam. Here we have a ASME steam. Steam. It's a Molière chart. It's a set of rules set in the software to translate the Molière chart. Yeah. Steam table, normally we use steam table, right? That table is here. It's inbuilt.
Any other queries? Any other queries? Shall we close the session? Okay. EDR or HDRI is better one? EDR or HDRI is better one?
Yeah.
Maybe for the last question continuation, I think.
Okay, this is a very good question. In fact, EDR is from Aspen ICs. It's a recent tool. It gives a high level sizing, but HDRI is a real tool. Before we construct any exchanger, better to run in HDRI. EDR is for preliminary sizing, I can say. So we have a many engineering design phase. We can do EDR at basic phase, but when we do a front-end design, use HDRI.
Any other queries? Any other queries? Shall I close the session? Okay. So now I request Shweta of final year to deliver the vote of thanks.
It gives me an immense pleasure in proposing this vote of thanks. I would like to be thankful to our management for giving permission to organize this webinar. I extend my gratitude to our honored speaker for his giving elaborate explanation on the simulation techniques for equipments with standard codes and for the ideas on different softwares used in chemical industries and opportunities. Thank you, sir, for your wonderful session. I would like to extend my heartfelt thanks to our beloved HOD for his constant support in organizing this webinar. I extend my heartfelt thanks to our coordinator, staff members, organizers for their efforts towards this webinar. I'd like to thank all the participants from various colleges for active participation. Thank you all.
Thank you, Shweta. Thank you, Mr. Subramani sir, for the wonderful session and practical explanation on various softwares and giving all these queries patiently. Thank you very much for your and extend a support future for our students also. Thank you very much.
Sure, we'll do that. And thank you for giving me an opportunity to present to our juniors. It was nice to have a discussion and interaction with you.
Thank you very much. The feedback link for the participants is posted in the chat box. So do fill up. You automatically get your certificates. Thank you, participants. Thank you, all students, for making the session. Thank you. Thank you, everyone. Even if you're from other colleges also, definitely you will get a certificate once you fill up your feedback link.
Ma'am. Ma'am. எப்போ ma'am?
Your test will be by 2 to 3 p.m. for final year.
2
okay.
to 3, yeah.
2 to 3 p.m. for final years. And for third year and second years, you will have test by 11 o'clock. Okay.
எங்களுக்கு 11 o'clock வச்சிருங்க ma'am.
Question paper is not yet ready. So 2 to 3 p.m. Okay. Shh.
பயம் இல்ல உனக்கு. ஏரியில ஆடுதான்